Okay, I guess let's get started. So welcome back. So today's lecture is going to be on asymmetric numeral systems. So let's just go over the quiz from last time. So last time we learned about arithmetic coding, and the quiz question was again around a Bernoulli random variable, which we have been now seeing quite a lot, where probability of A is P and probability of B is just 1 minus P. And you were asked to consider two symbols, AB and BA, both of them to be encoded using arithmetic coding, right? And the first part was, do the code words for AB and BA have the same code length? Yeah, okay, I see a couple of nodding heads, and that's indeed correct. I think most of you got this right. In our case, both probability of AB is going to be P times 1 minus P, which is same as probability of BA. Just if you want to write it, right, exact. And as Shubham discussed in last lecture, the code word length just depends on the interval length, which depends on the probability. So in this case, both of them will have the exact same code word length. And then the follow-up question was like, does our arithmetic coder output the same code word? Yeah.
On 1.1, a minor point is the upper bound of the code length depends on the probabilities.
Yeah.
In practice, for a real arithmetic coder, the code lengths might be different by up to 2 bits. So that's why in the question, I think we added a statement that you have to assume an idealized version of the arithmetic coder. Otherwise, it's not actually strictly true.
Yeah. Thank you. Yeah. Good point. Is that clear? So what Shubham just said is like in the actual, if you remember, like the code word length actually was so this was like the bound for our code word length, and so you'd actually need an idealized compressor which can do this, and in this particular case you can work out the exact probabilities, right? Okay. Yeah, continuing, the second part was like, do they output the same code word? And the answer there is obviously false. They are both, like if we look at the 0-1 line interval, AB and BA would go for like the different regions. Sorry, let me just expand it out. Right, so your BA would be in this region, whereas your AB would be expanded out in this particular region, right? And so they are just different code words. Quite straightforward. Any doubts on that one? No, okay. So continuing on the second part, so then we basically gave you some probability distribution over symbols, and gave the probabilities, and then given an input bit stream and an input of length 3, we ask like what's the decoded sequence. So it's a very standard arithmetic decoding. You guys just had to go back and redo what we learned in the class. So in this case, I've already converted this bit stream corresponds to 0.60935, and so all you need to do is repeat repeat the decoding procedure, right? So our A contains 0.5 mass, B contains 0.25, and similarly C contains 0.25, and your number is somewhere here, right? So the first symbol you will output is B, okay? And then you zoom in and you repeat again, divided into 3 intervals and find the point. And if you keep doing that, you basically get the BAC as your output code word. Yeah. Okay, any questions on arithmetic coding before we get started with ANS? Cool. Before we start, I just want to give Kedar a shout out. Most of the slides are similar from the last year, and so just wanted to give him credit. Okay, so last class we learned about arithmetic coding, and there we learned about that given any distribution P, your arithmetic coder achieves optimal compression. And one really important point there was like what arithmetic coding allows is to separate the model and entropy coding part. So you can come up with a best model for whatever for whatever system you have, right? You can come up with the probability for those blocks. And then the entropy coding part takes care of ensuring that the lengths basically have this bound, which we just looked at, right? Like in the class. So basically allows you to come up with a good model separately and then just use the code as is. Okay, which was not something we were able to do in Huffman or Shannon or any of the previous codes which we looked at. This also meant that it can work very well with changing distribution P. In fact, you can come up with like adaptive algorithms which adapt to your changing data distribution using arithmetic coding, and that's going to be a topic which we'll learn in, which we'll get to, I think, in 2 lectures from now. We'll show some concrete examples there. And yeah, we had like, there are various variants of arithmetic coding in practice, which you will find mostly depends on how we break down the ties, how we basically have an efficient implementation of the encoder and decoder. And basically arithmetic coders are used like everywhere, right? Like, so again, we'll see more and more examples of this in future lectures. But then what's the issue, right? Like, so, these were discovered sometime back in 1970s. So are we done? Like, is lossless compression a solved problem? Interestingly, no. So again, I think Shubham talked about it in the last lecture, but if you look at the compression, so this is bits per symbol, lower is better. Arithmetic coding does much better than Huffman coding. Again, it was because like you can imagine the whole block length, whole data is part of the block length, right? But interestingly, when you compare the speed of arithmetic and Huffman, like both the encode speed is lower as well as the decode speed is lower, and actually quite lower, right? And dependent on the application, you might actually want to trade off the compression you can get with the speed, because you might just have to deal with a lot of data very fast. And these numbers are from Charles Bloom's blog, which is like very interesting. And so today we'll learn about RANS and TANS. And if you look at the compression for RANS and TANS, they have basically the similar compression performance, but they have much higher, at least decompression speed. Like we'll come to the encode speed, but if you look at the decompression speed, they have like much higher of magnitude, right? So if you were to compare something like TANS and Huffman, they basically have very similar decode speed. TANS has much higher encode speed than arithmetic, while it performs almost similarly, though with some slight overhead compared to arithmetic in this particular example. And this is the reason why we want to even study these codes, right? These are like really efficient. And basically, like, so these were discovered, I think, around 2014. And if you look at any compressors today, they basically use, a lot of practical compressors today use some version of ANS. So ANS is basically a class, it's a class of compressors. It's not really a single compressor. And for example, RANS is one version, TANS, R stands for range, T stands for table. These are like 2 extremes of this family of compressors. But there are like various variants of ANS out there. And basically they have replaced arithmetic coding and Huffman coding in various places depending on the application requirement. So for example, RANS is basically just a drop-in replacement for arithmetic, but it's going to be faster. So if you care about the compression performance, you might want to do this while getting advantages over the speed. Similarly, TANS is actually a drop-in replacement for Huffman. But now, in its case, like it's almost as fast as Huffman, but it gets much better compression, right? So it's like, depending on your application, these algorithms are a direct clear win to be like, they have the best properties of Huffman or arithmetic. Okay. So now that we understand like these, there is something missing in the kind of code, in kind of encoding strategies which we have learned, and there exists something. Let's try to understand it a little better, like how it works, right? And so this has a very funky name. It's called asymmetric numeral system, which in itself is a good question, like why do you call it asymmetric numeral system? But even before we start with asymmetric numeral system, let's start with a symmetric numeral system example, which actually all of us have seen in real life, right? So suppose you have inputs as digits, just single digits, 0 to 9. And let's say you want to encode this, right? So some data stream, which comes from the alphabet 0 to 9. So let's say your data input is 3, 2, 4, 1, 5. Okay. Can you form a single number X which represents this data input? I heard a yeah, sorry. Yeah. How would you do that? Like, how would you represent, like, if you knew these were like just digits, how would you represent this as a single state and tell your friend? You would use this, so the student answered, you would use it as a digit of one number. Exactly. You can encode this as just 3, 2, 4, 1, 5. Right? And if you think about what this 3, 2, 4, 1, 5 really is, like, what was the encoding operation you did? Can somebody answer that? Sorry? Yeah, so the answer was like use like the base 10, which is exactly the idea here. Like you will use base 10, but now you have to think about your data will be input as a stream, right? Like, so we are looking into a streaming kind of code, right? So you would start with 3. But exactly like you said, we'll see how we can form this. So let's say you start with 3. So that if that was the only thing, you would just represent it as 3. Now let's say you receive the second symbol 3, 2. Okay. So the way you would do this is just multiply it with 10, add 2. That's 32. That's exactly the decimal 10 expansion of this thing, right? Now let's say the third symbol you receive is 4, right? So one way to think of it is again like decimal expansion, right? 3 times 100, 2 times 10 plus 4. But you could have also thought of this as just 32 multiplied by 10 plus 4, right? And does this give you an idea of basically forming like a streaming encoder for this thing? Right. So the idea is very simple. At each point, you maintain some initial state. That's the only thing you are maintaining. Okay. When you receive the first input 3, you just multiply the previous state by 10 and add the new input, right? That's the only thing we were doing. That's the decimal expansion of, so as to say this thing. And you keep updating your state. So when you receive 3, your next state is 3. After you receive 2, it's 32. And so on and so forth. So 320 plus 4, 3240 plus 1. And you keep doing that to get the final state, 32415. Okay. Now suppose your friend comes to you and gives you this state and asks you, like, what was the symbols which were encoded? Can you do that? This is exactly the next question. Yeah. Exactly. So the solution which gave was I'll start with this 32145 as my initial state. I'll divide it by 10 and calculate the modulus operand, right? And this will give me this will give me 3, 2, 1, 4 and 5, right? And then I can keep repeating this operation. So in this particular case, the by 10 operation gives you the previous state, right? So this was the previous state from which you got your new state. And the modulus operander gives you the symbol. But now you see something interesting. When you do that, you will actually get 5 first, right? Then 4, then 1, then 2, then 3. So, basically, your decoding runs in exactly the same fashion like we just talked about. Your decoding runs in the exact same fashion we just talked about. So you just do modulo 10, you just find the integer part as well as the remainder, and you keep recovering back the state which you had and the symbol which was encoded the last. So when you start with 32145, you'll first get symbol as 5 and the previous state as 3214. Again, you divide this by 10, 3214, you continue this, right? And you know where to stop because either you were told the number of symbol or you get back to some initial state where you started from. So the encoding process started from s equals to 0, you recover that and you can stop that. Okay, I got back to my initial state. Okay, nice. So now if we were to write it as a decoding step and an encoding step, what did we do? We actually did nothing, right? Like, so you are maintaining a state which you are going to output. You are maintaining a state which you are going to output. Whenever you encode a symbol, you multiplied the previous state by 10 and then you added the symbol. Okay. During decoding, you start with some state x. You decode the symbol by first taking the modulo operanda, right? And then you update the state by just dividing it by taking the integer part by 10, right? And then your decode step kind of needs to return both the symbol as well as the state so that you can continue this step. Nice. And like we said in this procedure, the symbols which you get are in opposite order, right? So when you encode it, you went from encoding 3 to 2 to 1 to 4 to 5. But when you are decoding, you are coming in opposite order. Okay. And in each step, you are able to recover the exact same state, which were used during the encoding, right? So when you went from encoding, you went from, like if you just look at the state, you went from 0 to 3 to 32 to 3214 to 32145. But the decoding was a reverse process. You started with 32145 and each step you recovered the same state. Is it clear? Okay. So far very simple, right? Like very simple idea. All of us have used this in some fashion, one way or the other. So this is exactly like the symmetric numeral system encoder. Okay. There is one last piece missing. Like we never converted our things to any bit arrays, right? Like we just left it at this number, this state to be encoded. So the last step is basically just transmitting the final state X in binary using something like CLOF log 2 x plus 1 bits, and like similar idea as what Shubham discussed last time. And so if you now look at the complete encoding step, right? So remember this was our base encoding step, which was just multiplying by 10 and adding the symbol. And then if you have a data input which you want to encode, you'll start with some initial state, which was 0 in our case, like when we started. And then for each symbol in data input, you just encode your symbol and you update your state. Okay. And finally, you just output the binary form of whatever your state is. So at this point, we have a complete encoder, right? Like it gives you a bit stream out. And you can losslessly use to recover the original bit stream. And then when you are decoding, you are just reversing the each step, right? Like encoder and decoder are exact reverse of each other. So the decode step, first of all, you are converted into some uint from the bits, right? So that you get your final state. And then again, you have your symbols, and for all your symbols, you'll do this decode step over the state, returning you a symbol and state. And you will append the symbols in a list, and you'll keep doing that, right? It's occurring in a streaming fashion. Finally, the thing which you need to be careful about is you need to reverse the symbols. Otherwise, the order of symbols in which you are returning things would be wrong. Okay. And now, in this case, we have an encoder and a decoder which are exactly mirror image of each other. You can ensure that they will always do lossless encoding, decoding, right? Okay. So we have a lossless compressor. Okay, even before we go there, even before we go to the next slide, any ideas about like what kind of compression rates is this compressor able to achieve? So as a hint, let's just look at the encoding step, right? What are you doing? So your symbols are always in your symbols are always 1 of 0, 1, 2, whatever, 9. But what about X? As you keep encoding more and more and more and more symbols, what's happening to X? It's very simple, no tricks.
It keeps on growing.
It keeps on growing. By how much?
Approximately 10 times.
Exactly. So now what you are doing is your state is going to 10 times state X at each step approximately. And your state is continuously growing. So this number X is always, after a point, it's always going to start dominating S. Right? So roughly, for each symbol, the price you are paying is to encode a number which is 10 times the previous number. And so you are paying roughly log2 to the base 10 extra bits per symbol. Now this only happens once you have encoded a few of them, like the first few symbols, this won't be true, but you'll reach that stage very fast because your symbol is just limited in 0 to 10, whereas remember in our example, your state keeps on growing, right? And this is exactly the idea. So at each step, your state X is just becoming 10 times the previous. And so roughly per symbol, you are paying these many extra bits. Correct? And so in this particular case, a compressor actually is an optimal compressor for symbols which are in 0 to 9 if we assume that the symbols were uniformly distributed. Because no matter what the symbol is, you are paying roughly log 10 to the base 2 extra bits to encode it, which will be the entropy in this particular case. Great. So in some sense, we have already, we have found a very nice compressor, which works well for uniformly distributed symbols, right? You can think of how you can generalize it from 10 to something else, like it need not be just 0 to 9. Any other numeral system would do for you, right? So that's good. But this compressor is only optimal if you have basically each of these symbols have probability 0.1, right? It's uniformly distributed. Does anyone have any guesses what we can do if, let's say, this was a non-uniform distribution? Yeah, any guesses? Why was this optimal? Let's just see this again, right? Let's leave it here. So it was optimal because my state was being multiplied by 10 at each step for each symbol, no matter what the symbol was. Like why 10? What does this imply? So another way to think about this, right, is the extra price I am paying at each step was this. And so far in the class, over almost every class we have talked about, this is like one thumb rule you live by. Like if you can get a compressor which gives you lengths around log to 1 by p, you have done the job. That's like the best thing you can do with this compressor, right? So now with this thing in mind, can somebody take a guess? Like what would you do if these symbols were, I don't know, coming with like 0 was coming with probability 0, p0, 1 was coming with probability p1, so on and so forth. That's a good guess. So the guess which was said here was like, okay, maybe we want to multiply by a smaller number. But why smaller? Why not bigger? Let's start with, yes, I do want you to multiply by something else, but what was this 10 really, right? Again, it's not arbitrary. It's actually the value of log of 1 over p. It's value of 1 over p, right? So what you would want to do for when you have different probabilities really is somehow have some equation which can give you maybe something like this, right? And if you can do that, then roughly whenever you get a symbol PS, we'll discuss the details how exactly to do that, but let's see if we understand the idea. And if you can do that, then no matter what symbol PS, when it gets encoded, you end up paying an extra price of just log of 1 by PS approximately, right? Which is the best thing you can do. Is everyone with me? Like if we understand this, we have at least understood the basic idea of the asymmetric numeral system and what we are trying to design, why it might work. So again, instead of scaling x as 10 times x previous, we want to scale it as something like 1 over probability of s at each step. Okay. Is everyone with me? Cool. So now let's see how exactly RANS does this. And to do that, let's introduce some notations which will be useful. So we'll consider probabilities which can be written in terms of integer frequencies. Okay. What that means is like if you have a probability, you can write it as frequency s by some integer m. Let's take an example, just to be clear. So let's say you have alphabet, which is 0, 1, 2, and your probabilities, which are 3 by 8, 3 by 8, 2 by 8. Okay. In this case, I'll represent this as a list of frequencies, which is 3, 3, 2, which is just taking the top terms here, right? And m, which is the common denominator, 8. Okay. And we'll also, as we have seen, I think, even in arithmetic coding and before, something which is really nice is an object to keep track of is the cumulative probability distribution. And we'll keep track of something parallel of that here. So we'll keep track of the cumulative frequencies, essentially. Okay. So the cumulative frequencies in our case is like, so frequencies are for A3, B3, C2, and so a cumulative frequency array, is that visible? Yeah, okay. It'll start from 0, plus you'll add the previous one, 3, plus you'll add the previous one, 6. So just summing the frequencies up till that point. So this object will be useful as well. And so this is, so in code terms, somebody was like, they were not able to think, how do I write it in code terms, right? Like, okay, I understand approximately I need to multiply it by 1 by probability s. Okay. But as we were seeing in symmetrical numeral system, right? We'll basically do the exact same steps. So if you look at the encode step, it's going to be the exactly same. You start with some initial state for each symbol in data input. You run this base encode step, which we are calling, which takes in the previous state and the symbol and updates the state. And finally, you're going to return the binary form of this. Right? And so the only thing which has changed is this base encode step, which was previously, so previously what was this? So previously it was just 10 times x plus s, return x, right? Now we need to update this thing. So given this notation, any ideas what we can do to get this? It's not that hard. Yeah, go for it.
Well, we could take the ceiling of whatever probability S and then just apply the hint, but I'm not sure how you would decode that.
Perfect. So the answer was we can maybe take the ceiling of Fs over M instead of probability S, but we are not sure how do we decode that. That's a great point, and we'll come to that. But this is the base encode step in case of RANS. And what I want you guys to, so this is, I'm giving it to you. I'm not right now justifying all parts of it. But if you look at the part which is just focusing on the X previous one, what we are doing is we are taking like the the integer division with frequency S and then multiplied by M. Exactly what the student suggestion was, right? Like I need to divide it by probability. Let me take the integer division by Fs and then multiply it by M. Okay. And then we add a bunch of other stuff, which we'll discuss in 1 second. Okay. But basically here, now you have ensured your state roughly increases by 1 over PS at each, whenever the symbol S is being encoded, right? Yeah, and so let's just focus on this step now. Let's just see. Let's work it out together for a few examples so that we really understand what just happened. So this again, I'm repeating because like I like to remember it like this base step. It's always good to go back to the symmetric numeral system to see how this is coming from, right? So previously it was X previous times 10 plus symbol. And so now this 10 part, let's take this 10 part is being replaced by something like this, and this plus symbol part has been replaced by something like this. Okay. Let's just work out some examples and then we'll see if it makes sense, how we can use this to decode, right? So let's work out the example for this particular setting where let's say you had the alphabets which we have been discussing, 0, 1, 2. And then your frequencies were 3, 3, 2, M is 8, cumulative probabilities is this. And so let's try to work out the final encoding for 1, 0, 2, 1. Okay, so let's start. So your initial state, let me just say, okay, let's just do it. So your initial state is 0. Okay. At next step, you want to encode input 1. Okay. So let me use the same symbols which are used here. So your initial state X is 0, S is symbol, X is the state. So in the first step, let's just, when you are trying to encode 1, so now you get symbol 1. And so let's just work out the new state. So new state is going to be X previous by frequency S, just 3 in this case, times M plus cumulative of 1, which in our case is 3, plus X previous modulus of frequency S. So just writing down the operation, not doing anything funky here. Just like literally reading all our symbols which we have formed, all our notations, and just plugging it back. And so this gives your X as 3. So after step 1, your new state is 3. So step 0, step 1. Okay, let's do step 2 now. So now the next symbol you receive is 0. So your next symbol is 0. Now you start from the previous state. So your previous state is 3 and your frequency is, so for 0, for 0, I'm going to pick the first elements here, right? And so for 0, so for 0, the frequency S is just 3 times 8. Plus my cumulus is 0, and then again it's 3 modulus 3, which is 0. So this is 1, this is just 0, and so this gives your updated state to be 8. Yeah. And then you can keep doing this for each symbol which is being added, right? So at each step, you are updating the previous state based on the new symbol which is being received. Okay. So I'm working this out live for you, but we have this worked out in the slides in the neater format if you like that. But yeah. So this is just like going through the same operations which we discussed just now, right? Like just each step. And if you keep doing that, in this case, you'll get 101, let's say, as the final state which is being encoded. Before we go on, we'll decode this, but let's try to see the same formula for something which we have already seen, which is uniform distribution case, right? Over 0 to 9. Can someone work it out and tell me what it gives? Okay. I almost want to leave it as a homework. It's straightforward putting down the numbers. Actually, I'll do so. So you can like just work it out once you go home. This will actually lead back to the exact thing which we have been seeing so far. This will lead down to x previous times 10 plus s. So this is, and that basically would happen because, okay, I'm giving away the answer. This will always be 0. This will be s, and this by frequency s doesn't matter, so it's just multiplying by m. So I know this is fast, just work it out. It's like very basic divisions. Okay. So whatever this beast looking thing we came up with, actually in the simpler case leads to the exact same thing, where we started our lecture from, right? Okay, so far so good, but now we also have to figure out how to decode it uniquely, right? Like I haven't really told you how do we decode it. And before we start with that, let's have some observation. So this is our base encode step. Again, something multiplied with m, which was like 10, plus some other term, right? So let me just write it like that. I'm gonna call it the first term block ID and the second term slot. And so your block ID is just x previous modulo, not modulo, integer division frequency s. So just this term, that's your block ID. And everything else is slot. This is called slot. So these are just technical terms. You don't have to worry, but this is a slot. And so one way to think about what we just wrote, like the actual ANS formula, is writing your state update as block ID times m plus slot, which is very similar format of what we had previously. But let's talk about the slot. What can you say about the slot? Excellent. So the suggestion I got was, so if you look at the slot, right? So slot is just cumulus plus x previous mod of frequency s, right? And so this term, since it's a modulus operation, is always going to be less than frequency s, right? And cumulus, also it's always going to be greater than 0. So actually we got a nice tight little bound, which is, it's always going to be less than frequency s, and this term will always also be greater than 0 because it's a modulus operation. Correct? So what we got right now is slot is always less than, actually cumulus plus frequency, I can just write it as cumulative of the next symbol because that's the definition of the cumulative. And it's always greater than the cumulative of s. Yeah. Actually, there is an even looser bound here which you can follow, which is your the cumulative probabilities will always be less than m. right? And the maximum value of the cumulative will always be less than the total sum of frequencies which you have, because it's always going to miss the last symbol. And it's always going to be greater than equals to 0, because your cumulative probability is just sum of positive numbers. So these are strictly weaker than the one which we worked out before. But now does this give you a hint? So now what we have gotten to, combining point 1 and point 2, is that your X is block ID times M plus slot, where slot we know is always going to be between 0 and M. So does this give a hint of what we can do next? How can we retrieve the slot versus block ID? Exactly. So we'll divide by M.